Today we are going to use Nastran Solution 200 to perform an optimization of a composite laminate. My name is Christian Aparicio and I will be presenting today's topic. So this is our goal. We are going to take this composite tube composed of 8 plies. We're going to let some of these orientation angles and thicknesses vary. And so by the end of the video, this is what we are going to obtain. We are going to minimize the weight from 1.6 and we are going to minimize it to 1.04. Here's the original layup. Here's the optimized layup composed of 90 and 0 degree plies. Also, we are going to let the thicknesses of each ply vary, so you can see the change will go from 0.01 to 0.0065. One thing to note in this example, some of the failure indices are initially being violated, or rather, our failure index is experiencing failure. We are going to discuss how to account for this during the optimization so we prevent plies from failing. Now, here, just to quickly go over the agenda, we are going to have a few moments regarding the structural model. I want to communicate to you how to make sense of how the composite laminate is constructed. I know some of you might be new users to Nastran, you might be an actual student, so I feel this is very important to cover first. And then we'll switch to discussion on optimization. So I want to cover what the optimization problem statement is. This is something very important for any optimization, so that's why I want to cover this first. And then after that, I'll show you the exact procedure you need to take in Nastran to perform this optimization. So how do you take an existing BDF file and convert it to Solution 200? How do you specify your variables, your objective, and your constraints? How do you perform the optimization in Nastran? And after that, how do you view the results? And then at the very end, I'll walk you through the process of updating your original composite laminate with the optimized thicknesses and orientation angles. Now, just in case you are a professional engineer and you would like more information on Nastran Solution 200, you're welcome to contact me at this email address. If you have a question regarding training, any Solution 200 questions, or any general structural optimization questions, you're definitely welcome to contact me. Now, if you would like access to the web app, I do provide access free of charge for any student. If you're a professional engineer, I can also grant you access to this. Throughout each slide, you'll see my email address at the bottom of the slide, so feel free to pause the video anytime and send me an email. Now, let's go ahead and talk about how this structural model is configured. One end of the tube, if you will be allowed to expand freely in the radial direction. It will be constrained from translating in the X and Y direction, or rather, I will prevent it from being translated in the Z direction. Again, this end is allowed to freely move in the radial direction. In the inside of the tube will be a pressure of 400 psi. Now, this is where I wanted to cover. How is the composite laminate oriented? Here we are looking at the material coordinate system for this one element. You can see here the red arrow indicates the positive X axis and the green arrow represents the positive Y axis. Now, using the right hand rule, if you rotate in this direction that you see me highlight with the laser pointer, this is the positive orientation angle direction. If you were to go the other direction, that would be your negative direction for the orientation angles. And now here, if we were to have an 85 degree ply, this 85 degree ply would be from the X axis 85 degrees in this direction. So here you can imagine there's here it actually would be helpful if I use a pen. So here, this red arrow would be our X axis, and then if we move 85 degrees, this would be the orientation angle for the first ply. And the same would be repeated for each ply. This one's negative 85, so from the positive X axis, you would go negative 85 and you will land here. and you repeat this process again and again for every other ply. So this is one thing I wanted to show you, because I know some of you might be students who are watching this tutorial, and you might be sort of asking yourself, how are these plies oriented? So if you want to see how this coordinate system is laid out, you can go to meshing, go to show. Let me see if I can figure out where that was. I think it was under properties, show material orientation, and here, let's go ahead and plot all of these. So the tool to use is under utilities, display, and then plot material orientation. Here, let's go ahead and mark the X and Y direction, and we'll go ahead and select one of these elements that you see here. Let me just go ahead and delete the old plot. And here you can see the positive X and the positive Y coordinate axes for the material coordinate system. So again, to access this plotting tool, you will go to display and plot material orientation, and then here you can set the options and just pick all the elements that you want to do this for. So here I'm holding the shift key to select multiple elements. So that's how the laminate is laid up. In addition to the orientation angles, we also are focusing on the thickness of each ply. We are going to let let me take a step back and see if I've discussed this. This is actually the first discussion of our optimization problem statement. The optimization problem statement is composed of three things. One component are the design variables. What exactly are you varying in your finite element model? Here we are going to let x1 be a design variable that corresponds to the thickness of lamina 1. We are going to let this thickness variable vary from 0.001 and 10, and we are going to do this for x2 for thickness 2, x3 for thickness 3, and so on until x8 for thickness 8. We are also going to have design variables for the orientation angles of the plies. X9 will correspond to the orientation angle of the positive 85 degree ply, and we are going to let it vary from negative 90 degrees to positive 90 degrees. We are going to repeat this for each additional orientation angle. And then one specific thing, at the end, we do not want to land on orientation angles that are not in increments of 5. So for example, if we land on an orientation angle such as 81.35, we don't want to land on orientation angles like that. We want to land on orientation angles that are in increments of 5 degree plies. So here we're going to impose a requirement that says, if you do end up at a ply like this, perform an operation to land on a ply like this, 80 degrees. Alternatively, you can land on something like 85 degrees. So here, this is known what is called discrete values. And I'll show you how to set this up in the optimizer in a moment. One other thing, design variable linking. We want all the plies to have the same thickness. If we were to allow each thickness to vary by itself, we are going to get different thicknesses for each ply. So what we are going to impose also is a link. We are going to say that the thickness of ply 2 is going to equal the thickness of ply 1. The thickness of ply 3 is going to equal the thickness of ply 1, and so on and so on. Thickness of ply 8 will be equal to the thickness of ply 1. Also, we want the 85 degree plies to always have the same orientation angles, but they are allowed to have different signs, if you will. So here, for example, if X9 went from 85 degrees, and then at the end it became 20 degrees as an example, and this is a thickness of ply 9, then or this is actually the thickness of ply 8. So here what we were saying is, where's X15? Here. So this is design variable 15. We are saying that X9 becomes 20 degrees. So here, let me write 20. That means that X15, because of this link, will also be 20 degrees. Here we are saying that X15 will equal the angle of X9. So if X9 changes to 20 degrees, then X15 also becomes 20 degrees. And then we also have a second expression here that says X10 will be the value of X9 multiplied by -1. So here, if X9 is 20, then X10 will be 20 times -1, so that would be -20 degrees. So here what we are saying is, for the 85 degree plies, we want to have the same magnitude, but have different signs. For the set of plies that are 60 degrees, we want them to share the same magnitude, but different signs. And the way we are going to achieve this is by creating these design variable links. And I have the expressions here. And again, I will be demonstrating how to impose these linking in a moment. This is a quick snapshot regarding the optimization problem statement. We just had a discussion regarding all the design variables, and we just had a brief discussion regarding the design variable links. Now, your finite element model is going to produce what are called responses. It's going to produce a lot of displacements for the nodes. Each element is going to produce its own set of strains and stresses, and the list is quite long. This is your opportunity to specify which ones of these responses are going to be your objective and what are your constraints. So here, for example, your finite element model is going to have a weight response. Our objective for this example is to minimize the weight. Now, as for design constraints, we are going to say that the failure index is a response. We're going to say the failure index of lamina 1 is allowed to range between 0.001 and 0.9. And we are going to repeat this process for plies 1 through 8. We want to make sure that the failure index is within this limit. Anything beyond 0.9 would mean the ply is experiencing failure. Now, here's a quick summary. Feel free to look at this one slide. This is a fair representation of what we'll be using to configure our optimization. So now let's go through the process on how to configure this for Nastran Solution 200. We are going to start with the PDF file. It's most likely the case that you've already gone ahead and constructed your finite element model and your pre-post processors, such as I did here. So this will be our starting point here, just to show you. This is the PDF file that was generated. This is what we need to start the entire procedure to convert it to Nastran Solution 200. We will use the Nastran Solution 200 web app to convert this PDF file. All the variables, the objective and constraints I just went over, we are going to specify these in the web app, and then we are going to perform the actual optimization with Nastran. Towards the end, I'm going to show you how to review the results both in the web app and your pre-post processor. And then at the very end, we are going to update the composite laminate with the updated orientation angles and thicknesses. Quick comment regarding the Nastran Solution 200 web app. This is available if you're a professional engineer. This is also available if you're a student. If you want access to this web app, my email address is here at the bottom of the screen. Feel free to send me an email and I'll work with you to get you access. What this web app lets you do, it lets you import a Solution 101 PDF file and it lets you convert it to Solution 200. Now let's go ahead and walk through the procedure regarding this. It would be worth to have the optimization problem statement shown up. So the first thing you want to do is to go to the web app. So here I am on the web app. Make sure you click on the size web app. This is what's going to let you specify the thicknesses and orientation angles of the laminate as design variables. We'll go ahead and select this first PDF file. It would be worth actually opening this PDF file. And this PDF file is an entire description of the finite element model, all the loads, the locations of the nodes, your material properties, the composite properties. It's all included in this one file. This file has to be converted to Solution 200, and we are going to do this with the web app. So after I selected the file and upload it, here is a long list of all the properties I can set as design variables. Here I am interested in selecting the following thicknesses and orientation angles as design variables. So here, just bear with me while I select all of these as design variables. You can go ahead and click these design variables one by one. So here, if I click on the plus icon for thickness 1, you can see that it's generated my design variable x1. You can repeat the process here. I'll click on the second icon again and again. But there's actually a faster method. Everything that you see here in this first page of the table, if you go under options, there's a button here that says bulk create. This, when you click on it, will automatically click all of these plus icons, all the visible plus icons for you. So here, if I go to the next table, I have my 8 thicknesses and my 8 orientation angles created for me. So now I can focus on specifying the bounds for these orientation angles. So here I'm going to say that for ply 1, I'm going to let the orientation angle vary between -90 and +90 degrees. And now for the initial thickness, I'm going to let that range between 0.001 and 10. Always be conscious of the lower bound for your properties. For thickness, as an example, there is no such thing as a negative thickness. But the optimizer, if its goal is to minimize the thickness, it will want to set the thickness as a negative number. And that will obviously cause issues for your finite element solver. So it's always important to know that if you're dealing with the property, that should always be positive, to add a lower bound to prevent that scenario where you have a negative value for something like thickness. Now, you might be asking, why am I only applying the bounds for these 2 orientation angles? If you remember the discussion on variable linking, all of these other orientation angles will be dependent on x9 and x10. So since these values will follow these values, I really don't have to worry about the bounds, since x9 and x10 already have the bounds specified for them. Now, before I go ahead and create those links, I'll go ahead and create the discrete values that I mentioned a moment ago. We want to say that we want to use a string of values between -90. And let me zoom in just so you see what I'm typing. -90 through 90 degrees, and we want to increment this in units of 5. So here, let's go ahead and copy that and paste it here. So this is actually generating a string of values from -90 through 90 in increments of 5. Alternatively, you could have typed in each value one by one, and so on and so on, but you can see that becomes a little tedious sometimes. So this is a shortcut if you're working this on your own. So let me zoom out and now focus on creating the design variable link. So here, let's go ahead and create a D-link. One thing I'll point out is that here on the right, all the bulk data statements that you need to specify your design variables are created for you automatically. So here, for example, let me go ahead and say that the thickness of ply 2, so that'll be x2, will be equal to the thickness of ply 1. So here we are saying that thickness or design variable x2 is equal to design variable x1. If you look at the previous table, there's a column called label. This is the label that's used to indicate the design variable for the specific property. So here, x10 is the second orientation angle, or rather the orientation angle apply to. So here, let's go ahead and continue the process. We also want to say that for x3, x4, all the way to x8, we are saying that x3 is equal to x1, x4 is equal to x1, and so on until x8 is equal to x1. And here you can see the dealing statements are created for me automatically here on the right column. Let me zoom in so you can see what happens over the next few moments. Now, this was the link for the thicknesses. Let's focus on the orientation angles. So if you remember here, we're saying that x15 is equal to x9, so x15 equal to x9. And then here we are saying that x10 is equal to -1 times x9, so let's go ahead and type that in here. x10 is equal to x9, and here the factor is -1.0. We also want to apply this to x16. You can create a new D-link entry to do this. I recommend just using the same one and typing it there. Now let's go ahead and look here. x13 will be equal to x11, and that will be a 1. And then I believe we have one more, x12, x14, x11, -1.0. Let me go back here and just inspect I've done this correctly. Great. So let's zoom out. So just to quickly recap, I've created design variables for the 8 thicknesses or the 8 plies. I've created design variables for the 8 orientation angles. I've also specified design variable lengths. I want to say that all the thicknesses will be equal to the first plies thickness. There are links between the 85-degree plies, and there are links between the 60-degree plies. Now this completes the creation of the design variables. The top bar, let's go ahead and jump over to the objective. You'll notice that in the top bar I have variables, objective, and constraints defined. That's why it's always important to have your optimization problem statement. Once you have your design variables planned out, once you have your design constraints and your objective planned out, it's just a matter of coming to the web app and following the workflow in an organized fashion. So here I'm in the objective section, and here is the one response for weight. Click on the plus icon, make sure it's minimized, and that completes the creation of our objective. Let's go ahead and move over to constraints. So here, let's look at this long list of responses. I'll go ahead and look for failure. If you click on the plus icon for composite failure criterion, this is what's going to let you constrain the failure index for this one ply. So here, let's go ahead and set this to element. And we want to specify that this constraint is applied to the failure indexes of the direct stresses and strains. You'll notice there's an option for the interlaminar shear stress, but we want to apply this again to the direct stresses. Now this is going to be applied for lamina 1. And as for the element here, we're going to only focus on one element. The reason we can do this is because it'd be worth looking at the results. The model is constrained in such a way that each element will have the same failure index. So here, let's go ahead and plot some of these failure indexes. Let me turn off averaging here. So here you can see we are looking at the failure indices for ply 8. The failure indices for ply 8 are all 21.7, as you see here in the spectrum. Let's go ahead and look at ply 2. And here too, it's 21. Let's look at ply 1. Same, and then ply 3. Here we have 14.2. Here, the important thing I want to communicate is that this model is constrained in such a way that each element will have the same failure index. This is good for us because we don't have to constrain each element in the entire model. We can just constrain one element. And the one element I've decided for this example would be element 1. So here, let's go ahead and type in 1. In your situation, if you want to constrain every element, what you can do is switch this to pcomp. And here you can type in the actual pcomp ID number. It would be worth showing you how to obtain that. So if you open the PDF file, you'll notice that here's the pcomp entry with all the thicknesses and orientation angles. This number in the second field is the ID for this pcomp, and here the ID is 1. If you accidentally press 2 or 3, the web app will caution you saying that PID does not exist. But here, if I say pcomp 1, it finds that this pcomp does exist in the PDF file. So if you want to constrain every element, you say pcomp 1, and then this will constrain each element associated to pcomp 1. Let me go back and actually switch this to element 1. So element 1. And again, we want to let this vary between 0.001 and 0.9. And we are going to repeat the process 7 more times, 1 for each ply. So here, let's just go ahead and quickly do this. One thing I'll say while I'm doing this, my email address was provided in a slide earlier. If you have any questions, comments, if you want access to the web app, you're definitely welcome to go ahead and shoot me an email. I'll definitely get back to you with instructions on how to get access. If you want more training, my YouTube channel actually has a bunch of tutorials. This is actually perhaps the 3rd or 4th version of this tutorial I've done. So if you want to watch me do this tutorial in a different way, perhaps I'll answer some of your questions you might have. You can also go to my YouTube channel and search for the same title, and I believe you would be able to find my older versions. Now here, I've gone ahead and repeated the process to create 7 additional failure index constraints. Here, let me glance at this and make sure everything's been configured properly. Everything looks good. So now let's go ahead and move over to the exporter. So the exporter is where you can download a package. It's a zip file. What's special about this package is that once you extract the content, there's one shortcut where if you double click that shortcut, it will trigger Nastran. So Nastran is actually running the optimization. This also opens the web app so you can monitor the process. What design cycle are you at? If there's an error, the status page will catch it. If it's successful, it will then load the results for you, as you see here on the screen. Let's first inspect the final message in the F06 file. You can see that here it says 2 messages. The first message says, run terminated due to hard convergence at an optimum. This, with the green checkbox, indicates that the optimization has gone through successfully. Here you can see the objective plot. We have convergence because the value essentially leveled out towards the end. The second message, a hard, feasible, discrete design obtained. Remember that for the orientation angles, we don't want to end on orientation angles that are between integers. We want whole number values for the orientation angles. So here, an example, if the orientation angle is 81.3, we don't want that. We want this in increments of 5. So here, we expect Nastran to either produce an orientation angle of 80 or an orientation angle of 85 degrees. This could be for any other number, so it could be for 13.3, or here 13.4. Any other number, it's going to try and get you a value that is an increment of 5. So here, let's go ahead and go back to the web app and see what this message means. And hard, feasible, discrete design. So here we see we've gone through about 14 design cycles, but on the last design cycle, we see a D. The D stands for discrete. This is a discrete design cycle. Let me scroll down and you'll see what happened to the design variables. So at the very beginning, for X9 and X15, the orientation angle was 85 degrees. For X11 and 13, the orientation angle was positive 60 degrees. You'll see that by the 14th design cycle, X9 and X15 are now 7.1 degrees, and X11 and X13 are 0.59 degrees. On the discrete design cycle, the very last design cycle, you'll see that I actually have how do I say, an orientation angle that is in increments of 5. And you'll notice one interesting thing about this. Number one, the orientation angle for X11 and X13 is not in an increment of 5. So in a moment, we'll go and inspect why that is. But here, what I wanted to point out is that right before the optimizer terminated, it realized that I had to perform this round off. Now, it's not actually a round off. There's a different special method that's used. But here, just to make it easier, I'll say it's a round off. The round off, you can see why there's a sudden change in the design variables towards the end. Here, let me go ahead and go back and inspect the final objective, which is 0.16. Now here, it seems it's taking into account that for the 85 degree plies, it should use discrete values. Now, let's go back to variables and look at our work. Here, what I want to see is if I specified discrete values. Here it is. So here I made a mistake. The mistake was that I applied my discrete values to the X10 design variable, which is a negative 85 degree ply. I actually meant to apply this to a 60 degree ply, so that would be this one. So here, let me go ahead and move over the bounds. And I believe everything else should be the same, right? So now let's go ahead and close these old windows and download this package again. And let's go ahead and run this optimization again. The reason I'm doing this is because it'll be worth opening up the web app again. For the original or the first optimization we performed, only the 85 degree plies were landed on a ply that was in increments of 5. But the X11, X13, basically the 60 degree plies, landed on values of 0.59, which is not correct. I found my error. I performed the optimization. Here it's loaded the results for me. And now let's go ahead and see what we have now. So at the very end, I get plies that are 90 degrees for X9 and X15, and for X11 and X13, I get 0 degree plies. So here, if I move a little lower, here you'll see the plies that are 0 degrees. Now, as for the thickness, you can see the new thickness, according to the optimizer, is 0.0065204. And here, let's see what happened to the weight. So the weight went from a 1.59 and it went down to a 1.04 as we intended in the optimization. So here, let's go back to the PowerPoint slide. And so far, I've discussed reading the status message and reviewing the results. You saw that there was actually an error in the first design attempt, and then I went back and corrected that error. At the end, this is what we obtained. We obtained a new design that is not 1.6 units of weight, but is now 1.04 units of weight. The new layup, instead of being composed of 85 and 60 degree plies, is now composed of 90 and 0 degree plies. The thickness went from 0.01 to 0.0065. And one important thing I want to mention, the plies. So if you will remember, let me minimize, or let me move this window. This was our original design. You can see that we have failure indices that are greater than 0.9. So these plies are experiencing failure. Let me load a new pattern window So here we'll go ahead and minimize some of these windows. I'll call this Pat 2. In this new window, I'm going to load the new structural results for the optimized model. So bear with me while I go ahead and do that. The optimizer, or rather Nastran Solution 200, is going to go ahead and produce new structural results for the optimized model. The benefit to me is that I can then go ahead and import the new results. So here, let's go ahead and import the original FE model. And then let's go ahead and attach the new results. So here, let's go ahead and click on Attach OP2. Let's go to the second directory and then click Apply. So then we'll go ahead and view the results like before. And here, notice that there are two sets of data here. There's a set D0 and a set D10. D0 stands for the initial design. So if we plot those results, you'll notice that these results are the same results that we have on the left. So here we have 21.7 for ply 8. Let me go ahead and switch this back to ply 8 on the left. So that's what the D0 stands for. These are the results for the original model. D10 stands for the results of design cycle 10. So here, if we look at that, you see that our new failure index is 0.9 for each element. And here, if I scroll through and select ply 5, here I have 0.175 for the failure index of this ply. So here, I recommend going through this procedure, loading your new structural results. The structural results are going to include results for the initial design, so D0, and the optimized design, D10. And the reason I encourage you to go through this process is just to make sure that all of your design constraints have in fact been satisfied. So let me go back to my PowerPoint slide and see what else is there left to do. So the last thing to do, your original PDF file has old data. So let's go ahead and minimize all of these windows. So this is my original PDF file. You can see that this pcomp entry is what's defining the thicknesses and the orientation angles for the initial design. I'm going to go ahead and create a new version, and here I'll just call it updated. And then I'll go ahead and open this on the right. We are going to replace this entry with optimized parameters. So if you go to the downloads directory, and then inside this Nastran working directory, there is a PCH file. And this PCH file has the updated properties that you need to update your original PDF file. So here, if you notice, on the left is that PCH file. Here is the pcomp term. This pcomp term is all you need. So let's go ahead and copy it. Here on the right, let's go ahead and delete the old pcomp term. And you can see that they are very comparable. This is pcomp 1. This is pcomp 1 here on the left. The same 13,000, the same hill failure criteria. That's all specified in both the left and the right. So now what I can do is delete the old pcomp entry here on the right and paste in the new pcomp entry. And there we have it. This file that's called updated, that's on my desktop, now has the updated thicknesses and orientation angles for this composite laminate. So that would be this file here at the very center of the screen. So there we have it. That is how you go ahead and perform an optimization with Nastran Solution 200 if you're dealing with a composite laminate. If you would like more guidance, if you want training, if you are a professional engineer, you're welcome to contact me at this email address, and I will definitely get back to you with a reply. Now, if you're a student or professional engineer and would like access to the Solution 200 web app, you can also contact me at the same email address and I will get back to you also. With that, thank you for watching.